get into this really technical deep dive. So one of the things that we're beginning to see in the market right now for AI is the fact that AI used to be idealized for what was an HPC type of stack. And if you look at this slide, we've gone from this point of being HPC simulation driven in the storage world to now we're beginning to see applications that have moved farther towards the right-hand side, research data management. And from that, you got into big data. And from there, it moved to AI factories and training and additional governance. And where we're beginning to head now is the idea that we have all of this data. It's been trained in all sorts of AI models, foundational models and things like that. And now it's reaching the point of how do you really use this data to surface real value into a customer environment, into a corporate environment, enterprises, research labs, and on and on. And we're seeing this show up in various use cases here, such as digital twins, surrogate models that are explicit for certain enterprises and use cases. And when we get into this space, we find that performance is really a very big problem. And so DDN, together with working with our partners at NVIDIA and a few others, have really been trying to figure out how do we go ahead and accelerate and make inference so efficient that it brings meaningful, high performance responses to customers and end users and researchers and so on. And so all these different types of challenges, as you can see on the slide here, are in place, and we're going to try and address them. So I think the next thing that we want to just discuss really quickly, just to level set, and we did this on a prior webinar a few weeks ago, is just to discuss KV caching and what it is. So KV caching really is this idea that you have a prompt coming in from an end user or an agent of some sort, and it goes through a whole series of computational functions that do what's called prefill. It computes what's called attention, and it brings all this data together, and then it wants to go ahead and store this data somewhere so that it doesn't have to recompute the data again and again. And then afterwards, the model takes this information, looks at this KV cache, and says, I'm going to apply this attention, look at it, try and find associations within the model, and then give you a nice response. And so that's really what KV cache is. It acts as this layer in between that stores an awful lot of this pre-computed types of information in this inference pipeline. Now, this example right here shows what it looks like for a single GPU owning the entire pipeline, but at scale, we're beginning to see this type of model where you may have tens or hundreds of GPUs, and really what you're looking for is a shared environment where all of them combined can look at this combined pre-computed attention and all of this cache. And there are certain technologies that are out there to take advantage of this. One of the ones that is becoming more and more popular is called Dynamo or Nixel from NVIDIA, and we'll probably discuss that in a few minutes. So I'm going to turn the slides off right now. I'm going to introduce Peter Bojanic, but I want to make sure that everyone understands as we go through this, if you have a question, please put it in the Q&A section, and we'll try and answer on the fly. And if we don't have the time, we will try and get back to you with answers as needed. The goal here is, now that we've gone through the very high-level statement, is that's the why KV cache matters. And Peter is here today to tell us how we can make this actually happen in a real DDN world. So Peter, being my partner in crime for this, I just want to say thank you for being here. You are a senior solutions customer. Please introduce yourself.
Thank you, Joel. And it's always a pleasure to work with you. Yeah, I'm a principal customer solutions architect at DDN. And my job is essentially working with our customers to solve their business challenges by leveraging DDN's technology portfolio. So that's EXAScaler, that's Infinia, and that's a lot of other things that we have in our shop.
Oh, fantastic. And again, thank you for joining me on this. Now, as I mentioned, I gave a really simplified, explanation of what KV cache is, maybe why it matters. But like I said, let's figure out, the details. How does this work, and how would a customer, implement this cache in an inference environment? So for KV cache, I show that really simple slide, but can you help explain what is the life cycle of the prompt as it goes through prefill and decode in order to get a response? What actually does get computed? I gave a really high level answer, but I'm sure you have many more details.
Yeah, I think you did a good job at kind of setting the stage for it at a high level. But let's dig in a little bit more deeply. I think one of the important things to understand is that the models themselves and the engines that serve them are stateless. That is to say that they've got all of the weights of the model and all of the training that is amassed from the data that was used to train the model. But your particular question and the responses that the model gave to you, and maybe some of the information that's used to augment the response, all of that stuff is stateless. Everything is passed in through the model as context. Context is the working memory of the model. So it's got its persistent memory, which is its weights. But then in terms of your interaction with the model, the working memory is this context. And from that context, tokens are generated, and then they move through all of the machinery that you outlined from a high level. That context is packed with a lot of stuff. It's the question that I ask. It is perhaps any information that was augmented into the prompt through a vector database, through some sort of similarity search, a RAG pipeline, so to speak. It's also the system prompt that you don't typically see, but it directs the model as to what to do. All the responses that have come back to me from the engine, all of my subsequent questions, all of these go into context, and it grows and it grows and it grows as we interact with the model. Okay, so that's, I think, the foundation to understand.
Okay, so when you do this, then all this computation probably has a significant amount of overhead, right? So when you're computing this attention and context, right, which is really what we're trying to get to here, what kind of when it does all this association, like what kind of impact in terms of computation does it have? I think you've talked to me before about it's actually like an exponential function in terms of how much compute is associated with any type of prompt.
Yeah, so let's talk about those two different phases. The first phase is what we call prefill, and as you pointed out, that's where attention is calculated. Attention is really just a lot of matrix multiplication. The prompt comes in, and then these matrices of vectors are calculated, the keys and the values and queries. Queries we won't worry about too much because they're ephemeral. They get calculated all the time. They get kind of discarded. But these keys and values that are calculated for the prompt stay consistent. So the next time you ask your question and all of that context comes back into the engine, all of the keys and values that were previously calculated, you don't really need to recalculate those again. It's kind of a waste. And interestingly, that calculation is quadratic in relation to the length of the context. So the longer the context, it takes substantially more calculations as that context grows. the next phase, after all that attention is calculated, then that gets passed on to the next phase, which is actually the generation. It's the part that we're really interested in. It's the generation of the content, whether it's the generation of an image or the generation of words that come back to you to answer your question. That's called the decode phase or the generative phase. And it's vastly different. It isn't subject to these massive matrix multiplications. It's much more memory bandwidth bound than it is compute bound. And so what we see is that the two processes, these two different phases, prefill and then decode, have vastly different resource requirements. And it's that K and V cache that's calculated in the prefill stage by attention that is effectively wasteful to keep recomputing every single time you want to ask the next question and all that context gets passed in again.
Okay. And so the KV cache is filled during the prefill stage because doing all this computation, and then afterwards the decode stage references and reads from that KV cache in order to pull the context into whatever the final compute, that the engine that's going to drive whatever the response is. At least I think I have that correct here. So let's start with the front end then. During the phase where it's doing the prefill, so you have prompts, you have agents that are creating prompts in some cases to put this all together. Is there an impact from, say, the total prompt length on how all this is computed? I mean, you mentioned it's a quadratic equation and we're doing lots of matrix math, but does that ultimate length have an impact on it as these queries and these prompts get more sophisticated?
Yeah, so the longer the prompt, and as we know, the prompt is going to grow in a chat transcript, in a programming environment. The questions that you ask, the responses and the code that come back and so forth, all of those things are going to grow the context. If we're using agentic workflows, then the initial question is going to come in. It's going to spawn a whole bunch of additional inference calls, propagating context. That context then is going to, is going to go through that generation phase. Content is going to come back and get consolidated into a response that's informed by the agents. So all of this is causing context to cascade and grow, and every time we pass it through this process again, whether it's a moment later when I ask my next question, or whether it's a week later when I pick up a conversation that I've been having with my chat agent and ask the next question about it again, all of that context needs to get passed in again. And if we can avoid recomputing, that costly process of recomputing all that K and V again in order to run through and get right to the decode phase, then we can save ourselves a lot of time. We can save a lot of time that appears as latency. So the end user's perceived responsiveness by the entire system can be improved because we get to actually giving them content sooner. And more importantly, I think for our customers, Joel, is that we're saving GPU resources. Because if we don't have to do these wasteful computations, then those GPU resources could be better directed towards new prompts that haven't been seen before. So we can do more with less. We can serve more simultaneous requests by keeping this KV cache around and retrieving it quickly.
So you sparked up what was kind of going to be my next question, which is, okay, so if you have this very sophisticated agentic environment where you have cascades of prompts, cascades of inference chains that are going down and need to be queried, it feels to me from what I've seen, and you being that customer success engineer, I want to see your view on this. It feels to me like the prompt chains, the inference chains are getting longer and longer because our customers are getting more and more sophisticated. They may have started basic, but they're getting there. And so we're seeing like token creation being driven up massively. We're seeing the inference chains. Can you correlate this? Are you seeing this happening at the customers that you're supporting?
Yeah, so I mean, there's two things that are happening simultaneously. One is that the models themselves, acknowledging that we have these new sophisticated workflows, are
Hmm.
implementing support for longer contexts. So you can cram more working memory into an individual inference request. So to give you an example, a lot of models, a lot of the earlier models might have taken a few thousand tokens.
Hmm.
Models in the last couple of years, it's not uncommon for them to support like 130,000 tokens or more. There are definitely models that are emerging now. They're in the million token range. Exponential growth in the number of tokens that the model itself can generate or can work with, both input as well as generate and send back. And then simultaneously, we have agentic workflows where we have these models with these that support these enormous contexts that are then we're proliferating the request, sending it out to broadcasting it out to a bunch of different inference workloads, consolidating that feedback and doing really sophisticated things. So those two
Yeah.
effects of larger contexts in large models and the agentic workflows that cascade all of this context are presenting a real challenge. Again, all
Yeah.
of it fundamentally, even in the presence of all this sophistication, there's still the mechanisms of prefill and decode. It always comes down to that, and it
Right.
always comes down to K and V, which are the working state that everything is generated from.
Right. So no matter what it does, at some point it has to come back and look at that pre-computed state. The model has to get in from either has to put data in, or the model has to come and pull data out to create the associations and move forward from there. So as this gets larger and larger, though, and the number of computations and the amount of KV cache that is being generated, these KV pairs and so on, it feels to me like it could have an outsized impact on the storage of that KV. Like, to bring it back to common storage terms, what kind of we'll talk about performance maybe in a little bit here, but
Sure.
what kind of capacity impact in storing all of these KV pairs? I mean, what does that look like from a from a pragmatic standpoint?
Sure. And Joel, I should also say that the entire industry is moving in this direction in a very
Yeah.
coordinated way. So our partner NVIDIA, who we work with very closely, we're working on Dynamo. Dynamo is
Right.
inspired by these larger models and agentic workflows. The recognition that you need to be able to scale up in an enterprise class way all of these inference workflows and all the stuff that we've been talking about with agents and prefill and decode, doing that in a really scalable way.
Yeah.
They're also working with leaders in the industry like the VLLM project and the LM
Right.
Cache project to embed technologies into those projects, as well as to make those various projects interoperable. So NVIDIA are acting kind of like a ringleader to bring all
Sure.
of those technology partners together.
Yeah. And
And this is where,
forgive
yeah,
me, forgive me for a sec, but VLLM and LM Cache really are kind of they're sort of the leaders right now in terms of the number of people that are using that to deploy their models, deploying their various um, AI pipelines right now. I believe that's correct.
indeed, the big three are um, NVIDIA's own inference engine,
Right.
and then the big other open source ones, SGLang and VLLM.
Yeah.
So those projects have been around for quite a while. They're well known. They're open source. A lot of our customers are using them. VLLM is probably the one of the most popular ones. And that's what our customers have been working with a lot. And LM Cache is the project that's grown up alongside of VLLM that provides this underlying caching capability and
Right.
all the pluggable interfaces to be able to interoperate with it.
Okay.
So
So sorry to
you
take
asked
it
about,
slightly off. Sorry to take it
yeah,
slightly off track, but let's bring it back then. So how does it relate to storage,
yeah.
capacity, things like that? I think was where we were kind of going for here.
Yeah, so let's take a popular model that a lot of our customers are using, the Quen 332 billion model.
Hmm.
If we were to pass, say, 100,000 tokens into that model, which is a very common test case for us, it's going to generate through this stack that I've described, through Dynamo, through LM Cache, through Nixle, and so forth, about 800 individual files. There's some tunables that influence this, but let's say for practical terms, 800 individual files will be generated from that request,
Hmm.
assuming that the context has never been seen before, and we need to cache all of the new KV at
Right.
once. It would be in excess of 800 files and about 26 gigabytes of data. So KV cache is big.
Oh,
It takes a
yeah.
while to it takes a while to compute. It eats a lot of memory, like 20 to 30% of the VRAM in an H100 GPU would be the KV cache for a given engine, and the storage for it is not exactly trivial. But the benefits of caching it and restoring it are substantial to the business. Again,
Yeah.
the
Yeah.
time to first token, the responsiveness that the end user gets to experience. So what do we get for giving 26 gigabytes of storage? Right, it's the responsiveness that the end user experiences, and it's the savings of the GPU cycles that I can be directing to do something else, serving another user whose prompt we've never seen before, for example. So we get a lot actually for that storage space, but there is a cost.
Yeah. Okay. So I'm just going to extrapolate while I'm thinking about this. So that was for, a couple 100,000 token input generated, like you said, 26 gigabytes roughly of data across 800 files. But now we're talking about tens, hundreds of users, tons of multimodal data, which could be inputs that aren't just, a few text documents, but it could be video, could be audio, could be research data. And then you have, hundreds of people searching it, hundreds of people prompting agents, which would then compound and so on. It doesn't take, I think, a lot of imagination to say that it would be easy to see something going into hundreds of terabytes, if not petabyte range for a KV cache store that could be used as to distribute back to all the GPUs and maintain that persistent memory of what the context is.
Yeah, it's
So
not
that's
unreasonable that a daily workload with modern types of models that have 130,000 token input could be generating K and V storage, KV cache
yeah,
storage in the range of tens of terabytes a day. And if we get into the 1 million context models, hundreds of terabytes a day, and that's just
right.
kind of rough guesses. So yeah, storage, it's a lot of storage to accelerate this.
It is, and I think you kind of led into this a little bit because so let's take a tiny step back here. I think we've described the problem and kind of like some of the benefits and everything in pretty good detail here. Um, and what I'm getting out of this that I'm hearing is that first off, if you're going to do KV cache, which is right now, as far as we can tell, for the next 3 to 4 years, probably the number one way of improving and accelerating an inference environment. So it's sort of becoming the de facto standard that everyone is searching for. One, you're going to need a lot of capacity. Two, and you mentioned it earlier, is that performance, low latency, things like that are going to really matter, especially on the decode side in terms of low latency. But you also need the amount of input because all of these GPUs are going to be writing into the KV cache
Yep.
as well. So there is definitely going to have a performance uh, function that we need to look for. Okay, so now that we shifted the burden for a lot of this recompute from the GPUs, it feels like we've pushed it onto the storage itself. The storage is now going to become the bottleneck to a certain extent in getting this all done. So from a real world perspective, to give the best experience in this environment, what kind of storage performance are we really looking at here to enable a really strong KV cache environment?
Yeah, so I won't talk in absolute numbers because of course it depends on what kind of scale you're doing, but
Yeah.
generally speaking, Joel, you
Okay.
need so again let's revisit hundreds of files for a single prompt. We're going to generate over 800 files. We're going to generate and those are going to be in the range of tens of megabytes, like maybe 33 megabytes each file. So what we have is a throughput challenge. We need to move substantial amounts of data quickly. We have an IOPS challenge because although 33 megabytes each is a fair size, it's borderline an IOPS challenge. We're not talking about large streaming. We're not talking about writing checkpoints, for example. These are much smaller files. So we have an IOPS challenge and we have a metadata challenge. So you need to be able to scale and perform in all of those dimensions in order to be able to be effective at KV caching. And fortunately, EXAScaler's architecture lends itself very well to solving this kind of problem.
Yeah, and I agree. I think EXAScaler is sort of the way to go. Highly parallelized. It's going to match up to that parallelized workload that is coming from multiple GPUs or a lot of multiple user prompts parallelizing what they put into it at the same time. Now, you did say something kind of interesting earlier, which is that you have throughput, you have IOPS. So throughput generally is, megabytes per second, gigabytes per second, terabytes per second.
Terabytes per second. Yep.
And that's easy to measure. At scale, we've seen this in a number of customers already. But the other side of the equation, IOPS, it's not just the number of IOPS, but it's the latency that's associated with getting all those out. So is latency really the largest issue here? And is that mostly on the decode side or the because it feels like prefill is more throughput and decode is more maybe I have it backwards.
That's okay.
Educate me, please.
Yeah, when you're trying to skip that costly prefill stage in the attention calculations, you need to get those files. You need to get that cache KV into the GPU. And this, by the way, is where Dynamo really comes into play. Is that Dynamo enables the disaggregation of those two functions. So conventionally, they would happen in the same GPU. You'd pass a request to the engine, and the same engine would do the prefill part, and it would do the decode part. And we could put in the caching function into that, and we could accelerate it. What Dynamo does is it allows us to separate out those two functions onto physically separate GPUs. So you could have a GPU pool that is targeted towards doing the prefill operations. You could have a separate GPU pool that is targeted towards doing the decode operations. And if you've got cache KV, then when the request comes in, Dynamo, with its constituent parts and able to talk about where the cache might be the warmest, is able to direct that request to the GPUs that are going to be able to retrieve that K and the V the fastest, skipping the prefill stage, going right to the GPUs, and then you need to load that KV into the GPU as quickly as possible, right? So this is where the entire stack comes into play. So we need not just a fast storage system that can deliver IOPS and can deliver throughput and can do massive metadata operations, metadata lookups of all these little files as we're trying to find the matching KV. You need all of that. You need a fast storage system. You also need a very fast fabric. You need to be able to move that data across the wire very quickly. and you want that fabric to be to support remote memory access. So you want like Rocky or IB, Spectrum X from NVIDIA, and EXAScaler supports those natively, right from the client. It knows how to talk RDMA over that. But it's not just enough to get it into the client quickly. We need to actually get it into the GPU's high bandwidth memory. And this is where GPU direct storage comes into play, and GPU direct object. But that's the mechanism that NVIDIA has got in place with storage vendors that enables that fast conduit right from the storage over the RDMA fabric, not just into the CPU's memory, but directly into the GPU's memory. So you get all those pieces, and now you've got a very fast conduit to get the data from your storage system directly in, no copies, no wasted effort, directly into the GPU's VRAM, where you can start to perform the decode operations on it as quickly as possible.
Yeah, I think there's a pretty good reason why nobody's building AI on top of Wi-Fi. We'll just leave it at that.
Yeah, sure. Yeah.
So, okay. So now we have the idea about the performance that's needed, the capacity that's needed, the full stack. It's time for the rubber to meet the road, right? We have customers who have EXAScaler. I think a lot of the people on this call may have, or who are on this webinar, may have an EXAScaler system that they're already using for various functions. How do you use EXAScaler to host a KV cache for inference? What are the actual steps that are needed to, if you wanted to do this and put it in place, how do you make it work? What is step one?
Mount EXAScaler on your DGX system or on your GPUs. It's actually surprisingly straightforward, Joel. Everything that we've talked about here today about the scalability of metadata, throughput, IOPS, support for RDMA fabrics, GPU direct support, that's been shipping on the truck for quite some time. So you don't need a new version of EXAScaler. We're not announcing anything new. It literally does it today with the EXAScaler that you got in your data center. There are really, the hard part is setting up the inference stack, and NVIDIA Dynamo helps with a lot of that, especially at an enterprise scale. So that's really the harder part you're going to have is figuring out your inference stack. But you literally mount EXAScaler, and you probably need to create a directory that is striped across all of your MDTs, because, as I said, we're going to create lots and lots of these files. So there's some good practices with again, features that are already in EXAScaler, have been there for a long time, and stripe your directory over all of your metadata targets, so you can make that directory as big as possible and get all the bandwidth of all the MDTs, and so forth. But yeah, that's about it. And then you tell it the directory that you want the cache to be read in, written to and read out of, and you're off to the races.
And that's it. Okay, so you set up your networking to talk to obviously your GPU systems. You go ahead and load the DDN client on board. At that point, you go into the back end of the EXAScaler system. You define, again, your striping directory. You define your capacity directory within the pools, and so on. And then at that point, you type the mount command, and you're done. So then you just define in that back end what capacity the mount will see, and that's it.
Yep, it works with all of the stuff that we have for multi-tenancy as well. So you can constrain, you can do all the magic that you can do with EXAScaler multi-tenancy with node maps and constraining, what portion of the file system and so forth. So it works with all of that. The tunings, the default tunings on the server and the default tunings that come with the client are good enough. There are some fine tunings that you can do to optimize things, but honestly, right out of the box, you'll get pretty good performance without anything special.
Yeah, and it sounds like the biggest tuning really is just to ensure that you do the striping across the MDTs. That's like the biggest tuning to really
That's
make sure that
absolutely
that
the yeah.
happens,
That's
because the rest of
if
it
you
is,
don't do that, you're going to run out of capacity on your MDTs pretty quickly. So so some sizing work and setting up the directory striping is probably the most important part to get.
sure. But again, it's not unfamiliar territory. This is something that is well known. It's well trod. And so if
Yep.
someone does this and puts the KV cache onto their EXAScaler, it's not like we're going down a new path of uniqueness here. These are well worn technologies that have been proven across hundreds and thousands of systems, and it's just a question of making sure that you expose it correctly to your GPU servers.
DDN is well proven with NVIDIA
Yeah,
DGX systems for training. We've been doing it for years, and there's a lot of attributes of EXAScaler that make it a really great architecture for doing training and fine tuning. And what we're showing customers now, as more customers are running their own inference in their own data centers, is we're showing them how EXAScaler's architecture and the features that are already there are also great for running inference and accelerating it through KV caching.
that's fantastic. So, Peter, I think we're beginning to run on time here. So I just want to say thank you very much again for joining us on this webinar. You've provided a lot of good, deep technical insight for those people who are actual practitioners, admins, the people who really want to understand how they can move from having an EXAScaler and using it for traditional types of workloads, like I showed on the left side of that slide, and moving more and more into that inference space. And as always, no matter how many times we talk on the back end, I always learn something new, which is fantastic. So with
Very good.
that, I invite everyone, please ask any questions, put them into the Q&A. There's a little tab in the upper right corner, depending on which platform you're on. And if we can't answer it on the fly here, then we will go ahead and try and get an email response back to you as we run out of time. Peter, thank you very much for joining me. And to everyone out there, have a great day.
Thanks, Joel.